So hello everybody, I'm Dániel Teubl. I'm going to talk about what I did as work in the past few years. As the title is Evolution of a Configuration System for UAV Actuator Monitoring. And, okay, just was a bit slow. So a few things about myself. I'm currently working as a research assistant at the Chair of Aircraft Design at TU Munich. I'm working with UAVs and flight testing and involved actively with flight testing activity. I used to write in my previous workplaces applications in C for bare metal embedded systems. Nowadays I am happy to write C++ applications, but still for embedded application. I'm also heavily working on test automatization, again for same systems. And on a personal note, I like reading different type of books, making good coffee, and this talk will be also about my personal journey from writing C programs to more than C++. And you can also follow the talk on your phone or via website via that link. But also I will share later on the source code and the presentation as well, so you will have more QR codes in the end. Bit about my workplace. I mentioned I'm working at the Chair of Aircraft Design with Professor Hornung. Our main activity is research in aircraft design related topics, which also involves working different tools. So that's also part of my colleagues are heavily involved with so-called Unicado tool, which is a customizable aircraft design tool written in C++. So if you're interested, you can also take a look. They will be really happy about it. Also on the layers tool, we are building, designing, and retrofitting different UAVs mostly for research purposes. And me and a couple of my colleagues working mostly with custom sensors and monitoring system. Just to show a few UAVs, they are not ended up like this, hopefully. So this is technically what we use almost every day during our work, and this is where we usually deploy our systems. And I'm going to talk a bit more later about the one on the right side with the straight wing. So a bit about the content for today. I'm going to introduce the system which we worked on with my students in the past few years, and look at different configuration scenarios for the same system. First, we start with the baseline and do an iterative approach that how do we build it up how do we did the configuration using a configuration file. And in the end, I'll show some snippets as well from a database like approach, and we'll do some takeaways. So about the system itself. We're talking about a small embedded system, which is main goal is to control and monitor actuators for small UAVs, small to middle UAVs. The main part of the system is STM32 microcontroller, and you can see it on the picture. It has some I2C sensors, which we can freely configure. It also measures voltage and current of the servo, and has a USB connection where we can communicate with it. And also important for us for today, it has an SD card where we can store some configurations files and log data. And the device itself looks like that. And a fun fact about the device, it's handmade, every piece, so there's a quite good variety in the quality there. So configuration is needed. About the test UAV, it's a 6-meter wingspan, 6-meter wingspan, 22 kilogram takeoff weight UAV. It has 6 actuators, which I highlighted. Each of them is monitored by the previously shown system. And all the time we measure the input reference signals, the voltage, current, and with different control surfaces, we also measure the control surface deflection, so we can get some scientific data there. And this is one of the assembly types which we use. This is located in the aft part of the UAV, and it's really hard to reach. So in some cases where you have to change the SD card is a lot of work, especially on the field. And in the front side, you can notice a lot of USB cables. It's quite ugly. Highly not recommend to do similar, but that's what we had. So right now, let's look at the different configurations. Start with the baseline. And what we will see on many slides, some version number and file name. So in the end of the talk, there will be some QR codes where you can find the exact same source code with all the rest of the functionality. I think this type of functionality is similar to most of us, at least from good old times. It's a simple main CPP, where before the main function, we define all the sensors as global variables and heavily use magic numbers to actually set the correct value. And it's also acts as a configuration file in some sense, because you just uncomment one variable or change the number, and already magically after a good build, you have a new functionality. But what I didn't like about it is if you can see the numbers in the middle of the screen, there is a nice equation as a constant. And to be able to configure that, you have to know that which board uses which resistors on the right voltage divider. So it's quite leaking some domain knowledge. But we're using some modern C++ features from the Chrono library, at least. Yeah, and during the development, so this was about 3 years ago, this state, or 4, we gradually build up testing toolchain where we can do unit and integration tests for the same source code. So it was supporting me and my students with refactoring activities. Let's look at an iterative approach where we try to push all the configuration variables into a config file. Which is easily done. It's already, right now, we are in the main function, in the initialization phase. We just create a config file, pass it into a class which will read the data from it, and we just try to find the right tag which we can supply as a status blink, and we use that variable to just modulate the blinking frequency of the main LED of the system. So it's a really standard procedure. For us, and when it works, I was, let's say, really happy. And some notes there for future, please rewrite it to better. A bit about the configuration file, it's a simple text file, human readable, so we can also change it on the fly when it's needed. And mostly uses key and value pairs. The third part is always ignored, it's just comment for the user. And sometimes for more complex sensors, it uses a bit longer configuration. So parsing it is not, so every type of this function needs its custom parser. A bit on the generalization part where we refactor that into more usable phase. We created a global variable, which is not good, but at least it's usable, called the defaults, which will actually store for us all the variables and parameters for the overall system. And beginning, we used as a global variable. Later, we try to inject it with the dependency injection to all the classes where we used it. And same aspect as before. We have the clean configuration file and read values by the key from the configuration by one. Update the parameter in the default data structure. And later on, we reuse that. So it's the same analog sensor what we saw on the first slide, just hiding all the magic variables later on. And from workflow point of view, if you don't know from the far, it's how much visible. The main idea that each function call just looks for one tag in the file. If you can locate the tag, then you parse the data behind it. Otherwise, you look until basically you pass that function and you go to the next phase. So which means in the buffer, the buffered config file, we actually really have to iterate a lot. The latest version, which was less than a bit about a year ago, in the main function, we cleaned up everything, wrapped everything into a simple function which handles the configuration update, and all the sensor initialization went into its own function. Yeah, and one thing which I need to mention here that at this point we already had some working software for the USB protocol. So it was possible to use feature flags at runtime on the system, so we was able to toggle different features on the fly. Yeah, I highlight it again. Good. How does the configuration looks itself? So we used in the end one function for each parameter, which hides all the complexity behind. But that also shows the problem with this approach, that whenever we introduce a new configuration, we have to write a new function to wrap it and introduce it to the list. If it's not there, but it's in the file, it's also a problem. But if the configuration parameter is not in the file, but the function is there, then you will not find it. So just the problems. So why I didn't like this back in the days, that whenever I have to change the code, there is a lot of boilerplate which I have to copy and paste from one place to another and revise a lot of things, and usually that lead to a lot of breaking as well. There was a lot of many steps which I have to do. I had a nice checklist, but sometimes you don't follow it to the point. And there was no compiler support for that version as well, so it was really easy to mess up something. And on earlier slides, there was a call for hitting the watchdog a bit to make sure that there is no boot loop happens in the beginning. I had quite a long runtime problems with this type of system. And yes, the biggest problem, there is only manual, changing the configuration file is only possible via manually. So I didn't want to writing a parser for the key and value pairs would be easy, but for the longer ones, it is, I wanted to skip it. And at some points, yeah, the domain knowledge is reflected back on the configuration file. So if you do not know, if you only want to change, let's say, a gain on for one sensor, you really have to do a lot of calculation to actually be able to write that gain into a configuration file. So it's not so fun. So after some studying and reading, I re-evaluated some choices and decided to do a design change and grab the problem from database point of view. But what was helping in the design change is that the USB functionalities was there, so it was possible to communicate with the system remotely, update the firmware, toggling feature flags, and requesting data stream and so on. But again, changing the configuration file, so you don't have to do all the feature flag updates in the beginning. It was not possible yet. And that was about a year ago when the test UAV, which we shown earlier, get ready. So we all the sensors installed, and most of the sensors was not reachable by hand easily. So whenever we need to change something or messed up something, that's minimum half an hour. And when you're on the field, that's not fun. And as I mentioned earlier, most of the PCs were built by hand, so that was a lot of variety in the hardware. So it wasn't so good. So I decided to do a different approach. The main goal was to be able to generate the configuration file on the system with the remote function call. So whatever is the current configuration, it should be able to pass it into the SD card, and whenever next time we restart the system, it uses that configuration file. And I decided to use a simple key and value pairs and build small data tables per simple types. We will see that soon. And I wanted to also see if I can introduce, just with test-driven development and constant refactorings, templates and different function overloads. And obviously, I wanted to learn to use those language features. And since I had problems with compile time problems and runtime issues, I wanted to make sure that compiler helps as much as it can via modern features. And I wanted to make sure that whenever we add the new configuration value, there is not much change what we can do. So it's wanted to make it easy. Yeah, moment. So this is how a simple data table looks like. I decided to use standard arrays because we already know the number of configuration parameters at compile time. So why not enforce that and be able to build some static asserts around it. And I also use the different enum classes for each key type. Currently this is for integer types, what we see here. And using the two, I was able to simply create some static asserts which always will do some compile error whenever there is a mismatch between the number of configuration points in the database or in the enumerations, for example. And how does it look like? So we have a simple enum class, one for each type. So we currently working with integers, floats, strings, and booleans. And each of those has a simple enum class. The last one is a not used tag to able to track it that how much val you currently are using up. Each of those type has a simple struct. So we can just populate it into an array. And for example, in terms of the integer classes, we can do minimum and maximum check at runtime as well to make sure if a user passes some bad configuration that it's actually handled. And it also holds the current tag and the key to be able to locate it. I used aliases, so I don't have to write that much from the arrays. And some static assert to make sure that at compile time the system works in a way we want it. And it's actually helped me really, really a lot. How does a configuration update looks like? So it's previously the configuration system class used and owned the file itself. In this case, we decided to not do that, just buffer up the configuration file content upfront and just pass it to the configuration handler as a string. It seemed a bit easier. So with this approach, we just iterate through every line, look for the tags on the key and value pairs, which is usually the first item, and find that the current line belongs to which table. And then call the simple change variable. And if you look at closer on the change, so I heavily use the overloads to make sure I have an overloaded function for each key type, so I can reference them back to the correct database. And inside that there's a simple stud find if, which will work to find the exact key. And then some boundary checked if we actually that's implemented. For integers it is, for booleans it's not needed. And then we call the simple implementation, change implementation itself, which is quite ugly switch case statement. But why I decided to use switch case statements to able to use the compiler support, which will tell me any time when there is a new value in the enumeration and it's not handled in the switch case, you cannot compile. So that's quite handy, although it's ugly because it's really, really long. Parameter change via USB, so via protocol, via custom protocol, just sending down the key and value pairs and using the exact same function call, which iterate through the same functionality. Works quite good. And if you look at the actual workflow, it's a bit more cleaner, at least I think. And if we compare the two, we can see that there is less branching, less visible iteration, at least. So me personally, I find the new iteration a bit better. And some of my slides are not visible. Yeah, and also I mentioned earlier, one goal was to make sure adding a new configuration point is easily done. So the compiler and the toolchain supports us. With the latest iteration, with the compiler support and other things, 2 or 3 points where the source code needs to be changed to add a new configuration. And most of that is writing a unit test. Some takeaways, some comparison on the size. So what we see here is all the different modules which were affected by the change between the last 2 iterations. And we can see that if you sum up all the differences, there is about 6 kilobyte, sorry, about 6 kilobyte gain we have on the new iteration. So actually we ended up with less source code. Any guess about runtime? Who thinks that the V12 something version runs faster? Well,
no. Initialization could be time.
Just looking at, let's say, just this loop, which is inside the middle. I measured that today, and I would be curious what you think that which is faster, the iteration in the left or on the right. So if it's the latest iteration, then so with more modern approach, let's say that way. Yep. I get surprised. I did some measurement, and the old version was about 1 second just to go through and update all the configuration points. The new version is 5 times longer. I do not know yet why. I was also surprised, so it will be a nice digging sometime later on. Some takeaways from the whole thing. I used data tables with key and value pairs and small data tables per type. What it allowed me to do is to use less conditionals and branching, and generalizing the overall workflow was a bit more easily done. So updating the code, adding new configurations was quite easier than in the earlier version. I heavily tried to use the templates, overloads, algorithms, and the lambdas. And what I found through this journey that one enables the other. So I started using templates, then I needed to use overloads to make the interface nicer. And algorithms enabled also lambdas, so it was a cool experience. And also I needed to write less code. So in the beginning, since I did a lot of refactoring, I did all the source code first and then make a generalized template from it just for the sake of exercise. But in the end, I wrote more code, but in the source code, it's less. And interestingly, I found my notes that using one standard stood find if over a simple row loop was a bit more heavy on the source code. But then again, it does a boundary check, and based on my notes, it actually saved my arts a couple of times. I wanted to put here earlier that although it's less size and less speed and more maintainable, now I have a big question mark there that always measure. That's also one mantra which I need to take. And yeah, compiler support is really handy, especially in this type of systems when problems can occur. And I also heavily use the CPP check and Clank ID. And I really like the refactoring, automatic refactoring feature of Clank ID. So just building up the new versions and adding more flags to be more strict helped a lot. Some references. All the slides, all the links are live to one of the booksellers. And you can download, you can use the source code or look at the source code from that link, and the slides are available on the other QR code. And if you have any questions, I will be here to the rest of the evening. And thanks.
Questions? Is microphone?
Yep.
Just take this one.
Is the speed the bottleneck or the size? I think more the size, no?
For me, currently the size, yes. It's more of a problem. When it's in the initialization phase, speed is also important, but not that much.
How much space do you have available?
The controller has 500 some kilobytes of RAM. Not much, but I am almost used it up, so I have like 10 kilobytes left.
Thank you.
Any other?
I mean, I have a question about the initialization. When does this happen in your application? Even before the flight, right?
Yes. So normally a flight is, so let's say a mission for us is 1 hour, half an hour, 1 hour. The direct flight component is usually, depending on the aircraft, 15 to half an hour, 15 minutes to half an hour. So we have plenty of time on the ground. We're doing ground test anyway. But if, let's say, one of these is going to boot loop, then we lose the measurement because we can observe it. But usually I will not break up the full mission if it's not the main goal of the mission to collect data with these devices.
And you don't read anything from SD card during the flight?
No. That's would be another talk how bad the SD cards usually are.
So have you reached the point that if it compiles, you are sure that the configuration will be correct?
Almost. I cannot be 100% because it needs to update the configuration file, so it's always an extra step there. But let's say my confidence interval is I'm 90%, 95% sure that it's going to work out.
Okay, thanks.
We have a question from online. Peter Lauro is asking whether you compared the amount of dynamic memory allocations, the allocations between the new and the old.
Not yet, but I will take in mind and we'll do that. Thanks.
Okay, so looks like that's it. So thank you very much, Dániel.
Thanks again.